All right, let's go ahead and talk through some of the information necessary to complete a selection of example test questions for test 3. These questions come from previous lab type activities. They're also based off of discussion questions. These are not all of the questions that you need to understand to make a perfect grade on the test. They are a good selection that covers most of the information. One of our big topics that we covered when we got started was density. So in the textbook, density can be represented by the letter rho. More often than not, I think in the lab it's referenced by the letter D for density. And then that's going to be for mass density, which is what we talk about most often. It's going to have mass divided by volume. That alone for this question can help you immediately eliminate some choices. So mass divided by volume means that we end up with kilograms divided by liters. So if you look, it's not possible for this one or this one to be the answer. From that, really, you should be able to narrow down and see which one you think is correct, but let's show the work anyway. So for the mass, we've got 8.00 kilograms. Sorry, my pen's acting up a little bit. Then 8.00 liters. So, as predicted, kilograms per liter, and then as you probably guessed from looking at the numbers, we get 1, or 1.00 if we keep significant digits the same. Now, this would be the density of water. So in this case, if we put an 8 kilogram block in 8 liters of water, then if it has a volume of 8 liters, this is something that we could take and move around. It would suspend in water. Okay, for the next one, we're going to use the same volume this time, but notice that we have a different mass. And so, we're going to get an associated density that goes along with this, and we'll be able to interpret again what we think this block would do if we put it in water. So let's start with density as mass divided by volume. For these numbers, we have a mass of 10 kilograms divided by the same 8 liters we saw a minute ago. Okay, so dividing these out, 1.25, and then kilograms per liter. Once more, if you were paying attention to the definition and the units here, you could have eliminated two choices. So liters per kilogram is not anything that's going to make sense for what we're doing right here. Okay, so now if we make sure we divide in the correct way, then we have this choice that is now more dense than water. So if it's more dense than water, then it's going to sink if you put it in water. So, this thing's going to be too heavy to float. It's going to sink. Then you might be able to guess what's going to happen with the last example in this group. So now we want to find density one more time. Okay, so for this one, we have a much smaller mass, and we have the same volume. Again, we can cancel by units, narrow down to a 50-50 choice. I think you can see that this is going to make more of a standard proper fraction here, but if we divide it out, then we can see we get a half a kilogram per liter. Now this would be some object that is less dense than water, and so if we were to put it in water, it would float on top of the surface, or rather half on the surface, half under the surface. Okay, and unfortunately, this next question in this format just looks like a giant mass of words. So our question cuts here, and then we have separate answer choices explaining what's going on. Okay, so if we read through this question, we have an 11-liter block that has a mass of 7 kilograms. So we can find the density of this right quick. Density is mass divided by volume. So we've got 7 kilograms over 11 liters. Now, because of the way the answer choices are set up, we would want to find this as a fraction and keep it that way. So we have 7/11ths, then kilogram per liter. Okay, now what this is going to do, if this object is less dense than water, so notice that this is less than 1 and water has a density of 1 kilogram per liter, then this is an object that would float in water. But some of it's going to be under the surface and the rest is going to be above. So let's think about this right quick. In order to displace enough water to create a buoyant force for this thing to float, if it's displacing 7 kilograms of water, then that means that 7 liters are under the surface. Okay, then whatever extra is being supported, and we would have 4 liters above the surface. So from reading these questions, we can narrow down. Technically, I guess we'll start from the bottom. This one's true. 4 liters, 4/11ths of the block rather, will be above the surface of the water. That is true. There's actually a lot we can gain from this, so we can eliminate this choice now. 7/11ths of the block will be underwater. That is true. Then this one's wrong because it's not 7/11ths that would be above the water. Okay, then this last one doesn't make sense because even though the 4/11ths of the block would be above the water is something that we determined, that's not the actual density of the block. The density of the block is 7/11. So then if we evaluate the final remaining answer choice where this talks about specific gravity takes the density of a material and divides it by the density of water. So we found that the density of our material, our block here, was 7/11ths kilogram per liter. Then the density of water is just 1 kilogram per liter. So if we show the work on this, technically we'd have 7/11 kilograms per liter over 1 kilogram per liter. Now, the number 1's not going to do anything terribly exciting here, but basically what happens is the units get canceled and we get this value back. And as it turns out, that would be the specific gravity of the block. Okay, so a little bit of a wordy question here, but easy enough concepts to sort through to find an answer. Okay, so let's say that we have a sample of water and, maybe it's not pure water, maybe it came from the faucet, maybe temperature and pressure are for some reason not normal, whatever. We've got water that we don't know the density of and we want to know the density. So same basic idea. Density is mass divided by volume. The mass is given to us in grams. Normally we wouldn't like grams, so that's fine here. So notice that our answer choices mostly include grams. We have 72.94 grams divided by the volume of 73.6 milliliters. Technically from here, you could already pick an answer choice. Milliliters per grams is backwards. We don't want the product of these, and it's not going to have no units. We'll talk about that case in a minute. So really, this is the only one that could be right. If we notice that this is a fraction, right, proper fraction where the top is smaller, and we divide this out, this thing seems reasonable. If we throw it through a calculator just to double check, we get something like 0.99103 blah 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 grams per milliliter. So seems like that one's going to do it. Then yeah, I thought I forgot to circle one. There we go. All right, now it won't bother anymore. Okay, here. So we want to use some information about a stopper and what happens when it's placed in a graduated cylinder with a water sample to find specific gravity. So there are a few steps that we need to pay attention to with this one. Some important things that are, common lab activities. So first we want to think about what specific gravity means. Specific gravity, often abbreviated because otherwise it's a lot to write down, is the density of your material. So in this case, that's going to be the density of our stopper divided by the density of water. Well, the density of water in these units is just 1 gram per milliliter. So that part we can technically fill in now. We don't know what's going on with the density of the stopper. So let's see if we can find that right quick so we can pop in our information and finish the question. So the density of the stopper is going to come from the mass of the stopper divided by the volume of the stopper. Well, the mass is clear enough. That was just given to us. The volume of the stopper, because it's a little bit of an unusual shape, is not something that we can easily stick a ruler up to and take some measurements and calculate. But what we can do instead is use what's called the displacement method. If we have something that will sink in a fluid, then we can measure the fluid before or after that object goes in there and use that to figure out how big the object must have been. So our volume from this one is going to be the difference between the two water levels of the graduated cylinder. So we've got 85.9 milliliters was the final reading, then 73.6 milliliters was the initial reading, and then that difference is going to tell us the volume of the stopper. So this looks like 12.3 milliliters, and then now we have plenty of information to find that density. Okay, so the mass that's been waiting patiently in the question, 15.64 grams, divided by the volume that we had to go get, but we do have it now, is going to tell us that we have a density here of, looks like 1.2715 grams per milliliter. Okay, so if we take and jump that back into our specific gravity formula, the number part's not going to have really too much of a change because we're dividing by 1. But you'll notice that the units are going to cancel and go away. So grams per milliliter cancel grams per milliliter. Dividing this out and then rounding will give us about 1.27. So this one, because it was a specific gravity, I'm going to underline it an extra time because it is important. Specific gravity is not going to have any units on it. So this was wrong and this was wrong because we didn't want any units. We specifically wanted no units. Now, if you knew ahead of time that the stopper was going to sink, then technically you could have picked an answer choice based off of that. It's going to sink if the density is more than 1 because it's more than the density of water. Okay. Then we want to determine the volume of a metal block given some measurements. So the measurements, if they come from a ruler, won't be able to have this many decimal places. They would have only 2. These would be measurements that were taken by something like a caliper. Because it's a block, we assume that it's a nice, boxy sort of prism shape. So we're looking at length times width times height. Okay, then we can, if we want to, eliminate some answer choices. You notice that we're multiplying together 3 things that all say centimeters. So it's not possible that we're going to get an answer back that's just regular centimeters. We're looking at centimeters cubed. And then paying attention to the fact that we are going to have to multiply all these together, then you might see what this might turn into, or at least you might be able to eliminate the other choice as too small. But let's work it the rest of the way out and see for sure. Okay, so as predicted, the centimeters cubed will come from those 3 being collected. Then multiplying this together, it's going to have a lot of decimal places in it. So let's write out some of those. Let's something like 30.56203, blah, blah, blah. And then if we double check what we use to multiply these, notice that all of these are the same size, right? So they're all 4 significant digits, and that affects our accuracy. We would have 4 significant digits on our answer. Wasn't a specific burden on this one because, again, this is clearly way too small. That's presumably the answer if these things were all added together. But if they're multiplied, in the first place, 3 times 3 is going to be 9 or a little more because it's got decimals on it. So multiplying by 3 again, that should have looked way too small. So there's our correct one. Okay, then now some information. Look, working on some ideal gas samples. So there is an ideal gas law. We don't specifically cover it. We cover a slightly modified version of it, or simplified version of it with some less information. So we have that pressure times volume over temperature makes some constant that changes depending on the sample of gas. We don't need to know specifically what sample or what constant that turns into for this sample, but if we have some information about one scenario and some partial information about another scenario, then usually we've got a pretty good chance of solving for something. Okay, so P1 V1 over T1, again, would make some number that we're not going to look for. but we're going to set that equal to P2 V2 over T2 and then see what we can plug in and what might be missing. Now, if we look, pressure is going to be kilopascals, and just because that's how this one's marked, and the other pressure is unknown, so we can steal what's here. So we'll have at the beginning 100 kilopascals. I'm not worried about significant digits here because these are already listed out, similar numbers of decimal points, and they're all considerably different from each other. All right, so the 100 kilopascals goes with a volume of 5 liters. So I don't know, 5.0. I guess we can keep that because it's not that much to rate. And then the temperature is 500 Kelvin. Okay, then find the new pressure. It doesn't say new pressure, but we had one before, and now we've got a new one that we're looking for. So we're looking for P2. Corresponding volume now seems to be 6 liters. So there's a little bit more space than there used to be. Think about kinetic theory and how the atoms and molecules are bouncing around off of each other and what that might mean for pressure. But we'll prove it here in just a minute. Then the temperature is still 500 Kelvin. Now that's actually helpful and something that could have given us a little bit of a shortcut if we'd looked for it ahead of time. If the temperatures are held constant, then they cancel from the formula and they don't really factor into what we're doing. This also kind of gives us an idea of what kind of equation we're going to have left over, because these things are next to each other, means that they're going to be inversely related. They multiply to give the same answer, so if one part goes up, the other part has to go down. So if we look, we don't know what the pressures are doing, but we notice that from here, the volume went up, so that means that my pressure is going to have to go smaller. So actually, I can estimate, or not even estimate, but narrow down, this is the only one smaller than 100, so let's see if that works out from the rest of this. Okay, then also if you want to, you can cancel out liters from each side and confirm that we are going to get kilopascals as an answer, kPa. And if we start multiplying, working through the numbers, I like to look at the variable first. So, if I can, 6 times P2, I don't really know what's happening, so I'm just going to write down 6 times P2. And on the other side, 100 times 5 is going to be 500. And then if I want to solve for P2, I'd have to divide by the 6 here. We decided earlier that this was going to be kilopascals, or kPa. Then taking 500 and dividing by 6, you get 83.3333, so on. And that reasonably rounds the answer choice we selected. Okay, then another one, small variation here. Because we're talking about a gas sample and we're excuse me, we're making some changes here, then we've got this same combined form that we can use to make some predictions. Okay, so looking at our initial set of conditions, pressure here appears to be 100, so 100 kilopascals. Corresponding volume early in the question looks like 5 liters. And then the temperature seems to be 500. Okay. Then, this time we know the pressure, so we still have 100 kilopascals. We have a volume of 6. Okay, similar to what we had before, but this time we don't know what the temperature is going to need to be to make these conditions work out, so we'll leave this as T2. If we look through the question and we process our information here, you can see that the pressure was held constant. So technically, we can leave that out from our formula. If you look now, these things are stacked like a proportion. And so that means that they are directly proportional or directly related. And that means that they're going to do the same thing. So like here, if I go from 5 liters to 6 liters, that volume goes up. But because this is a proportion this time, it's the ratios or fractions set equal to each other, then that means that the bottom's going to have to also go up in order to divide to the same answer. So just kind of an interesting little thing that we can pick out from the shape of the variables and how they interact with each other. Okay, so we can also cancel liters and liters Notice that we're just going to have Kelvin as an answer, but all the choices have that, so that should have been easy to spot. Technically, again, we can sort of eyeball the answer ahead of time. I did say that in this case, if the volume grows, then the temperature also grows. So the only one bigger than 500 is there. But let's work it through and see what's going to happen. It's a proportion, so a little bit ironic, but if there's an equal sign in the middle, straight lines, then the way we work this out is actually by going diagonally. So we'd have 5 times T2. Don't really know what that's doing, so all we can write for now is just 5 times T2. Then in the opposite direction, this diagonal is going to give you 6 times 500. So that is 3,000. And then now I want to finish solving, so I have to get rid of this 5 and divide. And so T2 is equal to 600. And we decided from earlier that was going to be Kelvin. And matches our prediction. Okay, so one more related one. This time looks like nothing is held constant, so it looks like we're gonna use that full formula. All right, so P1 V1 over T1 is equal to P2 V2 over T2, and then we want to start carefully plugging in and seeing what's going to happen. So initial conditions, looks like everything's all pretty much a bunch of ones and zeros, but we've got 100 kilopascals of pressure and 1 liter of volume, and apparently that's going to go to 100 Kelvin. Okay, and then later, find the new pressure. All right, so P2, that goes with 6 liters, so big change in volume there, but then 300 Kelvin. So there is also a change here. Notice though that it's not a proportional change. The volume here is changing more than the temperature. So think about what would happen if the pressure is given more room. Think about what happens when the temperature goes up, and then the pressure changes by a bigger factor, so it's going to have more control on the outcome. Okay, if we look at some of the units, then technically we can cancel Kelvin and Kelvin and liters and liters. We're looking for a pressure, so hopefully it makes sense. We're going to get kPa because that's how the other pressure was measured. Okay, and then once more, it's a proportion, so technically there's an equal sign, there's straight lines in the middle, and we end up working diagonally to work towards an answer. Be careful though, this is one of the reasons why I sometimes circle the diagonal, is you want to keep in mind that there's more than 2 things in this. So this is a slightly longer process than what you might see in some other proportions. Okay, but if I take 6 times P and then multiply that by 100, then I'm going to have 600 P. And we'll keep labeling as P2 to differentiate it from the original pressure we had. Okay, and in the other direction, technically we've got 100 times 1, but that's not going to do a whole lot there. And then times 300 is going to make this into 30,000. So that's pretty big. But now we're going to take and divide it by 600. And we decided that this was a pressure in kilopascals earlier, so I'll sort of ghost that in. And then 30,000 divided by 600 is actually 50. So smallest answer choice on this one. This happened because there was a lot more volume, there's a lot more room. So keep in mind that pressure is how the atoms and molecules are bouncing off of each other and then bouncing off the inner surface of the container they're in. If there's more room, then they're going to bounce off of each other less and bounce off of the container less, and pressure drops. Even though there was an increase in temperature, the increase in pressure was dominant. Okay, then this was something that we've talked about. At 0 Kelvin, we can't really get down to that temperature, but if we could, then that would be the point where all of the molecular energy is gone. There's no thermal energy, there's no wiggling and movement. It's beyond being a solid. So, the obvious choices are eliminated from these. A lot of times people will pick solid, but it's beyond being a solid because there's no motion left at all. And so that's something called a Bose-Einstein condensate, or we've abbreviated condensate. Now, this question really needs a modifier on here. It's important to say take any tiny action. So like if you have a huge change in temperature or a very large change in pressure or something like that, then very often you can end up skipping to higher phases or even just immediately causing an explosion and then, well, it's different anyway. But if some tiny action is taken on something that's at 0 Kelvin, then at that point it was a condensate. If you raise the heat a little bit, if you make a collision, if you change pressure, then it will give the molecules of the substance energy, a little bit of energy, a tiny bit of energy. And so that'll be just enough to make them basically wiggle in place and technically become a solid again. Okay, I made a brief mention of this one earlier, but if we're looking just in general terms, so without numbers here about what's going to happen between pressure and volume, then we can take our formula from before. So notice what's not being mentioned in here. It doesn't talk about temperature at all. And so we can get rid of that. So no temperature necessary. These things are multiplied with each other. And so because they're multiplied with each other, then we can rewrite this formula if we want to. And we're looking for a product. Well, to multiply to the same answer, if one part goes up, the other part has to go down. Because if both numbers went up, then obviously it would multiply to an even larger answer. If both numbers went down, it would multiply to an even smaller answer. But if there's a right balance between one number becoming bigger and one number becoming smaller, then you can multiply to the same constant answer. This type of arrangement, they're called inversely related, and called that because, like I said, if one thing goes up, the other thing has to go down. So important that you want to realize that these are going to do opposites. So if there's more volume, we talked about this earlier, then the molecules are going to bump into each other less and bump into their container less, and that's going to end up making less pressure, which should make sense. We said they're going to do opposites. If this is an increase, then we expect a decrease here. Okay, then similar concept, different variables. We want to think back to our formula again. Write out this, see what's missing this time. So we do have temperature. It's not the same as before. If we see, okay, well, it doesn't seem to be talking about pressure, then we can get rid of that. And then like before, notice that these are stacked in a ratio or fraction. So it's the quotient of these that we're looking to come out to be the same answer. So if you made one variable larger than another variable smaller, then you're going to end up moving those in different directions and you can't get the same type of answer. So like here, if this gets bigger and I'm supposed to divide and get the same kind of answer, this is also going to have to get bigger so that it cancels down and becomes the same type of result. So these are directly related or directly proportional, and they're going to do the same thing as each other. So if we look at what's happening here, if these are, like I said, doing the same thing, this says that there's a decrease in volume. So there's going to be a decrease in temperature. So normally we might see this in the opposite order. If we decrease the temperature, then the molecules have less energy. They're zipping around less quickly, and that will allow something to shrink back down. So if something gets colder, it typically gets smaller. They do the same thing. Okay, then one more of these, and then we'll look at something a little bit different. It's asking about pressure and temperature. So let's eyeball our formula, see how these stack and just kind of the shape of the variables that are left over to see what this is going to do. So if we look, see what's missing, this question doesn't seem to talk about volume at all. Okay, so let's mark that one out. Notice what's left over. These are stacked in a fraction, so this ratio or quotient of these is what we're looking at for our remaining formula. Okay, so if they are stacked like this. Once more, this is something that looks like a proportion, so we're going to say it's directly related or directly proportional. And then that tells us that whatever one variable does, the other one has to do the same thing in order to achieve balance. So we want to remember again, these are going to do the same. Okay, so if we increase pressure, then we are going to tend to increase temperature. So increasing pressure means more collisions, so more energy bouncing around. So, it's going to make the molecules tend to move faster on average. And so I think it does make sense. It's going to increase temperature. So increase here is going to mean that this goes higher. Okay, then if we mix different materials that are at different temperatures, then they're going to exchange heat. Now, there are a couple of things that aren't easy to determine. So if we have different types of materials, different temperatures, different masses, if everything's different, then we don't know how much the temperature is going to change. We don't even necessarily know that it's directly related to specific heat, because if you have a much larger mass of one thing compared to the other, then again, there's not a way to see how the temperature is going to change. So don't be careful here, or sorry, do be careful here. Don't fall for the trap. It might seem like I'm leading up to saying there's not enough information, but specifically the heat exchanged as sort of a conservation of energy, the heat itself is going to change by the same amount. So that's the only thing technically that we do know, is that whatever heat is lost from the warmer object is going to be heat that is gained by the colder object. Now, I don't know anything about masses or temperatures or final answers, except I know this very beginning idea, is that the heat exchange is going to be equivalent. So temperature will be different. Again, I don't know anything else about this, but this is just basically a conservation law. So that thing's going to be true. Okay, now I mentioned specific heat, talked a little bit about it just now and didn't really say what it was doing. Specific heat, the way that it goes into formulas, if something has a high specific heat, then it's going to end up having a high resistance to a changing temperature. In certain units, water has a specific heat of 1, which doesn't sound very impressive, but in using calories in these units, that's actually a fairly high number. Or if we use joules, then water has a specific heat of around 4.184, changes very slightly depending on temperature and pressure and a few other things, but around 4.18 or so. And again, that doesn't sound very big because it's, well, 4, but that is higher than most other things, especially metals. So water takes a long time, a lot of energy to heat up, change the temperature. Okay, so we're going to start with a very simple example. Let's say that we take two different samples of something or other and we mix them together. They can have different masses, they can have different temperatures, they can have different specific heats. And we can use this giant mega formula to see what's going to happen. So like I said, the only thing we know for sure is that the heat exchanged is equivalent. So we've got M times C times delta T is just our general way of figuring out how much heat is moved from one area to another. The mass of the material, specific heat of the material, change in temperature of the material, all factors in. Okay, so let's say we see that we've got water in both cases, then mass of my first sample, specific heat of my first sample, and my change in temperature of my first sample. I'm going to have whatever temperature is there minus the final temperature it comes down to. I did notice that the first one is warmer, so I know that one's going to come down. I want to subtract this in such a way that it stays positive, so I am going to modify my formula on the other side to keep the signs consistent. Okay, then I would have the mass of my second sample, the specific heat of my second sample, and my change in temperature of my second sample. Now, because of the way the sign changes go, I want to force this to stay positive. And again, I can adjust that a couple of different ways. But I do want to notice that this one warms up. So this is going to be final temperature minus the original temperature that sample 2 had. Now, what's nice about this, if we're looking through our information, It's a random ugly mass, but it's the same random ugly mass over here. So that can cancel from these. Because these are both liquid water, then on average we're going to say that they have the same specific heat because they're both water. In fact, I actually want to color code that a little bit better. So let me show that in purple. Because the substance is water, then again, those specific heats are going to match each other and they can be canceled. What's going to be left over then, they do have different temperatures. So if these have been the same temperature, if this has been 94 and also 94, then the final temperature would also have been 94. There was technically no heat exchanged. We just mixed together water with more water. If there's a temperature differential, then we're going to see that exchange of heat, and then we're going to see some new answer. So if we look in this, I also see that this is Celsius and that is Celsius. So it seems to make sense to me that my final temperature would also need to be Celsius, which is at least backed up by the answer choices. So really, I'm just wanting to work through my numbers here and see what this turns into. So my first temperature is 94 minus the final temperature that I don't know what it's going to get to. So, for right now, just 94 minus T. Then over here, it's that same final temperature that I still don't know, minus the original temperature for this sample, which was 52. Okay, and then now I want to start solving on this. So let's say that I collect my T terms, and then I also connect my constant terms, the plain numbers here. I want to move them and separate them. So that's going to give me 2 T's, and then the sum here, excuse me, I'm going to keep as separate pieces because I want to show exactly what this is going to do. Okay, kind of running out of colors though. I'll divide this by 2, and so my final temperature is the one temperature plus the other temperature divided by 2. So what I want you to see from this, and the reason why I didn't quite simplify it earlier, is this ends up being, we added 2 things and then divided by 2. This is just the average of the temperatures. Basically, because everything else was fair, same mass, same material, just different temperatures, then ended up really just being the average of these. Now from that, technically, you could eliminate this choice. It had to be somewhere in the middle. That seems a bit close to the 94 and a bit far away from the 52. But, from here, we can actually just take the average. So 146 seems to be the sum there, and then divide by 2. So it looks like it's going to be 73. All right, then we're almost done with this group. So important concept here. If we have the density of a material, then we can use that to work backwards and find some other information. So let's think first about how this formula looked. So density is equal to mass divided by volume. I've rechanged the scale a little bit here, the size of the variables, so I can stick this over 1. If I want to find the mass, and technically I have a kind of proportion here, I can cross multiply 1 times m is going to give me m, and then multiplying in the other direction, density times volume. Now where we have to be a little bit careful is that right now we don't technically have the volume. We have enough information to find it, and it really shouldn't be too hard to do. But we don't know it right now. So if we start plugging into this formula, then we have to keep in mind that we haven't finished this volume, but we can throw that into parentheses, just sort of save space and save writing to be a little more efficient here. The water level rose because of a block being put in there. And so whatever that difference is the displacement caused by the block and is therefore the volume of the block. Okay, and we can simplify this down. Density is still not really doing anything, but it's about to be ready to go. This volume, the difference here, will have 400. And then you can also see what the units are going to do. I should have changed colors there. Milliliters, cancel milliliters, that's 400. Slightly adjust my handwriting there. We're going to have grams left over, which is good because it is talking about mass. These are all in grams. And then I'm going to take 7.93 multiplied by 400. Then the only one answer choice really seems big enough, right? I'm taking 400 and multiplying by something more. We're going to end up with 3,172. Now, the concept here is an important trick because it builds into, in some cases, finding specific heats, finding masses, finding volumes. There's a few different ways that we can use this depending on the information that we have. So it's good to understand that knowing the density is not always the terminal step, right? Sometimes we start with that and break off in a different direction and find something new. Okay, so last one in the group, it is a little bit of a doozy. So we want to keep in mind that anytime we have a mixture of materials, we have that giant mega double heat formula that shows up. So let's see what we can do to sort of organize within that. The mass of my metal, the specific heat of my metal, and the change in temperature of my metal, which again I need to make sure stays positive to avoid some issues. But I'll take my high temperature minus whatever my final temperature gets down to. Okay, and then similarly, that's going to be the heat lost by the metal. That heat's going to be gained by the water in an equivalent amount, so I can set in the pieces and find anything that might be missing. So this is talking about the water now, so I'll have the mass of the water, specific heat of the water, and change in temperature of the water. So this one I want to do final temperature minus the original low temperature once more so that this stays positive. A lot of times you'll get a negative sign that you just kind of work out in another way. By intentionally flipping the subtraction on one side, we can fix that and never have to worry about the negative. Okay, so let's see what we have. We're supposed to start with the mass of the metal block. We don't have that, right? But we did just learn how to do that. So that's something we'll want to pay attention to. This right here is actually going to provide more information than it seems like it would at first glance. I suppose the first easy, obvious information is that this number alone, just the 600, is the original mass of the water. But then we want to think about this difference is going to become the mass of the metal. So mass of the water is just ready, but the mass of the metal is the displacement. That's going to be 900 minus 600, which is a nice clean 300. Okay, so that's a little bit better. Technically, it's not a mass, so you can't just plug that in directly. We need to organize a bit and see what else is going on. So thinking back to the previous question, we can do the density times the volume. Oh, I broke my own rule, didn't I? Yeah, let me fix these. Said the completely wrong word this whole way through. I'm sorry. Um, so yeah, these are volumes, right? Look at the units. So the volume of the water is here. The volume of the metal is here. We need this to find the mass, but we don't get it immediately. So yeah, even I was rushing this one a little bit and made that mistake. So oops, but we can fix it now. At least we didn't go too far. So these are volumes, and I can take the density and multiply. So density of the metal here, because it's talking about the block, multiplied by the volume of the metal, then that will give us the actual mass of this metal. So, oops, small mistake there, but we've got it at least before it caused any damage. But let's go from here. So now we've got 2.91 grams per milliliter, and that's going to multiply by the volume, 300 milliliters. Then it says find the specific heat of the block. So we are searching for this thing. So I'm going to throw a big X in the middle of this and even make it a different color so it's easier to keep track of. The high temperature of the metal was originally 100 degrees, and the final temperature came down to 24. Okay, so now the mass of the water. Now this one, ironically, is the same number. Water is used as the definition of a couple of things, but technically, at first glance, we don't have this information. So if we show our work, and if we're going to stay consistent, then 1.00 grams per milliliter for the density of the water multiplied by the 600 milliliters for the volume of the water. I think you can probably see what that's going to make. Conveniently, again, like I said, water is the definition of a few different things. This is going to be 1.00 calories per gram degree Celsius. So this is also a 1 because water's fancy like that, or potentially boring, depending on how you decide to look at it. Then finally, our temperature change. The water came up to 24 degrees. The original low temperature was 0 degrees. And I know this looks scary, but this is going to clean up very quickly, and then we'll be able to get to an answer. So we can look through a bunch of stuff with units. Milliliters here will cancel milliliters here. Similarly, these will cancel, which allows the grams to cancel. So that's already a lot of this gone. Then our Celsius units here will combine and cancel with these as they're combined. It's only units left I have now are the ones for specific heat from the water. So it should make sense that even if the number is considerably different, that the units on specific heat for the metal would be the same units for specific heat from the water. Okay, so believe it or not, that's a good chunk of the way to where we need to go. If we go ahead and multiply and simplify down in a couple of spaces, we can say that we've got these multiply to 873. Then we've got this x that we still eventually need to find. We're well on our way. We're just not there yet. And then this temperature difference, 100 minus 24, is 76. Okay, then this part will be simple enough. We're going to have 1 times 600. Technically, that's going to end up also multiplying by 1. And then this temperature change is nice and simple because it's minus 0. It's going to give us 24. Okay, I'm not worried about significant digits or anything here because these answer choices are clearly fairly far apart. I just want to work down and find value. We've even already decided what the units need to be. So let's continue chugging along. The right-hand side is probably easier. So if we do that first, we'll have 600 times 1, which is just 600, and then times 24 is going to be 14,400. Then this other side still has that x that we're looking for. So we'll drag it down, but we can simplify with these other numbers. So we can take the 873 and the 76 and multiply those. We get 66348. And then x is almost there. In fact, we'll jump to the color of the x. So we'll divide by 66348. We're trying to get this by itself, so that number needs to go away. Don't panic. The answer is typically a small decimal sort of answer. A lot of times students will think that's wrong and then flip it around and divide the other way, but it is intentional that we divide the much bigger number on the bottom in this particular case, and then we get some small decimal answer out of it. So from the calculator, 0.217037, so on, calories per gram and degree Celsius, basically just drug down from here. And then we can check and see, I'm going to circle in a different color just for visibility, but looks like this one. So be careful with the placement of the decimal compared to the other numbers. Notice that some of these are pretty similar to each other, just slightly shifted. Okay, and as far as the test 3 material, this ought to be most of what you need. So keep in mind that you also want to review any other assignments and then check the remaining discussion questions that weren't answered here as you're preparing. Remember that you can take the test multiple times, so try it. If you miss them, then come back and look at these questions, look at the other work, email me or your instructor if you need to. But otherwise, that should pretty much be it.